Hello friends, I Pankaj Dumka welcomes you all to this lecture on fluid mechanics. This lecture will be a very short lecture in which I will be explaining you about the path lines. What are path lines? So in last lecture you have learned about streamlines. So streamlines are what? They are the instantaneous lines. Okay, whereas the path lines are basically the lines which are formed by tracing the path of a particular particle. That means path line is the locus of given identity particles over a period of time. Okay, so as we are tracing the path, so they are tending to what? They are tending to Lagrangian concept, whereas streamlines were strictly Eulerian concept. And one more thing, streamlines are instantaneous. They are drawn at a particular instant. Okay, whereas path line as particle, let us say that this is one particle P1, it is moving from this point to this point. So while moving from this point to this point, this particle will be consuming some time. So time is inherent while defining the path lines. Okay, so what are path lines again? Path lines are the locus of given identity particles over period of time. Okay, so if this is one particle, so let us say this is another particle, this is also moving. Now the thing is, what you can see here is, if you concentrate on this particular point, then you will be able to analyze that this particular point now has two velocities, but this particular point is having this velocity v1 at time t1, that is when the particle p1 arrive at this point. So this is the velocity at this point, and when particle p2 arrive at this point, so this will be the velocity of the particle at some another time t2. Therefore two path lines can always intersect. There is no strict rules or harm in saying that two path line cannot intersect. No, two path line can intersect. Moreover, if a if a particle is, let us say you have a particle P1, it is falling back, means it is forming a loop, it is forming a closed path, then this is also permissible, because if you consider this point, okay, so at this point the velocity is v1 at some time t1 when the particle is arriving at this point, and when the particle is coming through this loop and then arriving at this point, the velocity here is v2. Okay, now you can very well appreciate the fact that these two velocities are at different times, because particle has to take some time to arrive at this particular point again. Therefore path line not only can intersect, they can also form a closed loop. So whereas streamlines, they cannot intersect, neither they can make a loop. So this is a very important point. So what we do in practical, in reality in lab, okay, so let us consider, I want to analyze the flow field which is there in this particular pipe. So fluid is flowing, let us say water is flowing. So what I will be doing is, I will be dropping some neutrally buoyant particles. Okay, neutrally buoyant means the density between of the particles and the fluid itself, they are the same. So at whatever place you are dropping these particles, they will be staying there. So what will happen if I focus my attention on this particular particle? So due to the motion of the fluid itself at this particular location, the particle will be moving in this pipe. So this is what the path of that particular particle, neutrally buoyant particle. So this helps us in understanding the flow behavior. So in lab coordinates, you cannot generate these streamlines, because these are the instantaneous line and they are mathematical, whereas you can generate the path lines with the help of these neutrally buoyant tracer particles. Okay, and when it comes to mathematics, and let us say you want to know the equation of this path. Okay, so that's not a very big deal, you can always do. Let us say that the field is defined by Eulerian approach, that is V is this, then velocity can be written as rate of change of displacement. Okay, now if you integrate this equation, okay, if you integrate this equation, then you can get the equation of the path followed by this particular particle or any particle in the flow field. Now, you can very well appreciate the fact that the knowledge of this constant can only come from some boundary condition. And what is that? This is basically the position of the particle which you are tracing at any specific standard or stipulated time. That is what you call as S naught. Okay. Therefore, this is a pure Lagrangian concept. So, this is what mathematically we feel about path line. One more thing, when the flow is steady, when the flow is steady, okay, when the flow is steady. So, in a steady case, the velocity ceases to be the function of time. Okay, if this ceases to be the function of time, and let us say I have a streamline, this is a streamline, okay, and I mark some points on this streamlines, and the tangent on these streamlines, these points on this streamline will give the velocity vector. Now, let us say a particle arrives here. Now, this particle, as the flow field is steady, so velocity at individual point will not be going to change with respect to time. So, if this particle arrives here, so this will be forced to move along the direction of this velocity only. So, in this way. So, if the moment it arrives here, this will be forced again to move in this direction. So, therefore, the particle path, that is the path of this particular particle, will be again this streamline only. So, in this particular case, when the problem is steady, the path line and streamlines are the same. Okay. So, in this lecture, I have explained to you that what are path lines and what are the characteristics of that path line and what will happen if the flow becomes steady. So, in this lecture, till this point only. So, if you like my video, then please do share, like and subscribe. Thank you very much. Take care.